All right. Well, we got a small crowd today because of finals, but welcome to our talk of the month. We had a break in December, but we're back again for the month of January. Tonight we have Sean Curry, who is an almost retired engineer who lives in Southern Oregon, just outside of Ashland. And he has been involved in astronomy for a really long time and has picked and choose from a lot of different areas in astronomy, including visual observing, astroimaging, and most recently some scientific data collection. And he's a part of some small telescope astronomers or amateurs, and they are observing red dwarf flare stars using photometry and spectroscopy. He enjoys teaching, or he just enjoys all aspects of science, especially astronomy though, and he particularly enjoys working with students and teaching about the mysteries of the universe. And with that, go ahead and take it away, Sean.
Thank you very much for that nice introduction. And I'm glad to be here tonight. I think some of you know that I've known Mr. Minato for a few years now up at Pine Mountain, where I've got the pleasure of meeting him and some of his family and some of his students. So it's a pleasure to be back with the group again. And I hope you'll find my discussion interesting tonight. Can I go ahead and share my screen? I will do that. And there we are. That coming up okay on your end? Looks like it. Good. So tonight I'm going to talk about spectroscopic observations of a recent nova. And that nova was RS-OPH, RS-Ophiuchus. And the main goal of this, there'll be some nerdy parts, some science parts, some observing parts, but the main goal is, I think, to sort of illustrate how you can do interesting science from your backyard, because this, in fact, was done last summer, late last summer, from my backyard with a couple of students from North Medford High. And backyards, especially for spectroscopy, don't need really dark skies. So even those of you in cities, some of the people I'm working with on the Red Dwarf project live in Phoenix, Arizona, and observe out of their backyards. So I hope you'll see that this is something that is open to just about anybody. And we'll learn a little bit about spectroscopy and novae and a few other things. And I suspect a lot of you know a bunch of this already. This weird looking diagram here is a spectrum. Some of you have seen these before, I'm sure, but we're going to spend a little bit of time talking about those as we go in. How did we actually get that and what does it mean? So I'm going to spend a minute talking about what a nova is, which again, I'm sure most of you know, but a little bit about RS-OPH because it's an interesting star. Talk a bit about the difference between photometry and spectroscopy, because in this case, we used spectroscopy to gather the data, although the Red Dwarf project, I'm using both of them. And then maybe what's most interesting to you is how the heck did we observe this star? What equipment did we use and what did it take? And most of all, what did we see once we were done observing? And anytime you want, excuse me, to ask questions, feel free. I don't think anybody's audio is muted, so just feel free to jump in any point here. We've got a nice informal group tonight. So what is a nova? Well, nova, as it sounds, is a new star. And the official definition is a transient astronomical event that causes the sudden appearance of a bright or new star that then slowly fades over several weeks or many months. And there are a bunch of different kind of novae. There's the fast one, that's a very rapid brightness increase up to 3 magnitudes. And I'm sure all of you have studied magnitudes in your astronomy class, that's a measure of brightness. And remember, smaller numbers are brighter, right? It kind of goes in reverse. There's a slow novae, which might take 150 days or more to decline. Very slow novae, which could stay bright for a decade or so and fade really slowly. And then what we're going to talk about with RS-OPH is a recurrent nova. And this is one that has 2 or more eruptions. And remember, a nova is a brightening of the star, and we'll talk about why that is. So 2 or more of them separated by, say, 10 to 80 years. These are quite rare. Only 10 of them have really been observed in our galaxy. So the fact that we were able to observe a recurrent nova only a day or so after it was first discovered was pretty cool. What is RSOPH? And by the way, you might wonder about the name. When you see, do any of you, have you studied variable stars at all? Talked about variable stars? When you see a name like RSOPH, well, OPH is Ophiuchus, that's the constellation it's located in. But when you see something like an RS, that means it's a variable star generally. And they started naming them as they were discovered in different constellations. So there would have been an A, a B, a C, a D. One of the other ones we're looking at is AD Leo. So that's an early one, AD. RS is a little further along. You can imagine this got pretty complicated and they started running out of letters and they couldn't use O's because they looked like zeros. Now, most of them have names like V787 Ophiuchus, but RSOPH indicates it's a variable star. And it's about 5,000 light years away. Its magnitude when it's not in nova is about 12.5. And if you remember, if in a dark sky with good eyesight, you can probably see maybe a magnitude 6 star, maybe 6.5. My eyes aren't very good. I can't even see those. So 12.5 is pretty dim, right? So you wouldn't be able to see it. However, it's a recurrent nova. This star erupts every 20 years or so, which is really fast. And there's a reason for that. And so it was predicted that it was going to erupt, and yes, in fact, it did. And what makes it interesting is it's a symbiotic binary system. So we've got a little tiny red dwarf, really dense, and a huge red giant companion. And the red dwarf is cannibalizing the red giant. It's pulling material off the red giant. And when it gets enough material, it undergoes thermonuclear reaction and brightens. So every 15 or 20 years, it's getting enough material off the red giant to erupt. One of the reasons that this is unusual and why it erupts so frequently is the 2 stars are only about 1 AU apart. And remember, the AU, the astronomical unit, is the distance between the Earth and the Sun. So imagine 2 stars, one of which is a red giant, that close together. I mean, these 2 are really close. And in fact, the material around the red giant is just being pulled into the red dwarf. Here's what it looked like when it erupted, and it got to visual magnitude. It was found very shortly after it erupted and became a very, very bright star and actually got to naked eye visibility. And here's a list of when it in the past, going back to 1898, a few of these were possibly missed because it was in solar conjunction, meaning the star was near the sun and you couldn't see it. But the last one we were interested in was 2006. That was pretty well imaged. And then 2021. So it was only 15 years between the 2 eruptions. This chart over here is what's called a light curve. So we've got magnitude with a V filter, which is approximates visual magnitude. So here we were down around 12 and a bit, kind of going along. This is within a day, it went up 6.4 magnitudes. So delta V down here, 6.4 magnitudes in a matter of hours. So this is an amazingly rapid brightening. And then a gradual decrease. Here's after 20 days. Still pretty bright, but gradually decreasing. So you can imagine it's been pulling this material, sucking it off that red giant, hydrogen and helium, and piling it on to the surface of that white dwarf. And it finally got to the point where all that material ignited in a thermonuclear reaction instantly in this huge eruption and brightening. Some people say that so much material is coming off the red dwarf, off the red giant, that it's not all being burned and that the white dwarf is gaining mass over time and eventually will reach the Chandrasekhar limit. Have you heard about that one? Do you know what happens at that point? The star will implode, right? it'll go supernova. So this is a very interesting star for that reason. There are not many recurrent novae that recur this quickly, and it indicates something very violent and unusual is happening. This is not an actual photograph that I took of the red giant and the white dwarf, but it's a little bit of an illustration. And you can see the white dwarf is actually tiny in here, but here's the red giant. Red means cool, right? This is actually a very cool star, very low gravity with this huge, huge balloon of material, envelope of material being pulled over by gravity. One thing is it doesn't land right on the star. It tends to go into this so-called accretion disk, and it's actually this material spinning round and round and round the star, and that's actually what ignites. So this is kind of a complicated diagram that I borrowed from somebody who gave a nice talk on RSOPH, and we're not going to look at all of it, but here's a couple of things. We've got the red giant over here, big, temperature of the red giant, 3,500 Kelvin. That's actually very cool. And you guys know, right? Red stars are cold, blue stars are hot. It's kind of the opposite of how we think about heat, but this is a big, enormous, cool star. But a luminosity that when you see this little symbol, L sub little dot, that's the luminosity of the sun. So it's got 1,000 times the luminosity of the sun. So it's putting out a lot of light. Here's a little tiny white dwarf over here. And what happens, you can see the material coming from the red giant gets to the white dwarf. When the white dwarf goes nova, this cloud of material goes out in all directions from this explosion. And eventually it collides with the material coming off the red giant. And we're going to look at that spectrum later, and we're going to be able to see this collision between the material coming off the white dwarf and the material from the red giant. So, and you can see the distance here, 1 AU. So these two stars are really, really close, right? I mean, no wonder the poor red giant's just being butchered by this white dwarf. So we observed this star with something called spectroscopy. So what is that? Well, photometry is pretty straightforward. That's when you measure the amount of flux or light coming off the star. So anytime you take a picture of something, right, you're getting, let's say with your DSLR, you're getting a measure of intensity. The bright things have more flux, the dark things less. Normally, if you're measuring photometry of a star, you'll put a filter in front of your camera, a visual filter, blue, red, infrared, so that you're only seeing wavelengths in a certain range. So you might want to see how much blue light's coming from the star, how much red light's coming from the star. Spectroscopy is a little different. It passes the light from the star through a prism or a grating and splits it out into all the different colors. So you get all the different wavelengths, and you don't just get 5 or 6 like this, you get thousands of different wavelengths. And a spectroscope then measures the intensity of the star at each wavelength. So we'll see that when we look at the actual spectrum graph later. So you can think of it kind of like photometry with thousands of little filters. So it's a really great way of looking at starlight. And in fact, most in astronomy, maybe most is a little strong, a lot of stellar analysis is done with spectroscopy. Radio telescopes too, but spectroscopy. And have any of you heard about a new satellite that was launched about a month ago? James Webb, right? By the way, I believe it went into orbit today around L2. So it's there. It has 2 spectroscopes on it. So most modern satellites for observing have spectroscopes on them. And the reason is that spectroscopy tells us a lot about the physics of the star and what elements are being involved in the different reactions. The light, the brightness is important, and looking at light in different wavelengths is good, but spectroscopy really breaks it down. So how did we observe RSOPH? It sounds like this is going to be pretty difficult, right? You're not just pointing a camera. Well, it turns out you need a spectroscope. I bought a spectroscope called the UVEX from a company called Cheliac. They're a French company that makes spectroscopes for amateurs and professionals. But you know what? UVEX started off as a 3D printed spectroscope, and I actually printed it myself, but then you have to buy the optics, and I didn't do that. I ended up buying the spectroscope, but it's a spectroscope you can actually make yourself from if you have a 3D printer. So I have a spectroscope, and we'll see a picture of that. You need to plan your observations. When are we going to look at this star? And I'll show you, I use Astro Planner, which is a really nice piece of software to do that. I'm not going to talk about a reference star much, but just be aware when you take a spectral image of a star, it's affected by the atmosphere, your camera, and your telescope. So it's going to have some systematic errors in it. What you do is you observe a known star at the same time or shortly after a reference star to correct for those errors. And I won't talk more about that. We don't have time to go into that today. I have a CDK, excuse me, 12.5-inch telescope on a plane wave mount, and I'll show you a picture of this. And I'm using an ASI 183 CMOS camera. So that's sort of regular, but as you'll see, there's kind of a difficult part to spectroscopy. And I'm using a bunch of software to guide the telescope and grab the pictures. The main problem with spectroscopy is keeping the star on the slit. And I think I have a picture coming up. I'll show you what that means. But one thing to think about is if you're going to observe a star, any star, whether it's a nova or anything, is it going to be visible at your location and at the time you want? So I'm using, this is Astro Planner, and I've set it back to the date, the 12th of August, when we observed this star in my location. And this line here is RSOPH. The main thing is that it tells me that at 8 o'clock at night, it's going to be at 37 degrees above the horizon. Normally, you don't want to observe below 30 degrees because of atmospheric effects. So 37 is good, and it's going to transit at 9:38. And I think you all know what that means, right? That's when it's going to be overhead. So I know it's rising starting at 8 o'clock, and it's going to be overhead. Now in the summer, of course, probably by 8 o'clock, it's still too light. But this little graph up here in the upper left shows you when it's going to be dark enough to observe. It also tells me the azimuth of the star. So it's going to be at 150 degrees. So that's southeast, right? And then I know, okay, it's going to clear the barn next door and the tree that's in my way and so on. So you always want to do a little bit of planning. Are you going to see the star? And by the way, the 12th was the second day of this nova. It was discovered the day before. We had already set up a session to work with the students, and just by chance, this nova came along. So here's my setup. This is a plane wave CDK. It's called a corrected Dalkirkham design. So it's got light comes in here, hits a mirror, bounces back, hits another mirror, comes through to the camera. So it's got a focal length of 2.5 meters. So it's a nice long focal length. This is the camera, the science camera, this little red camera. This is the spectroscope here, this black box. That's the UVEX. And I'll show you a little diagram of what goes on inside it. But basically, the light comes in through the telescope, gets split up by a grating, in this case, not a prism, into all the wavelengths, and then goes onto the camera. This little guy down here is the guide camera. That's what keeps the telescope pointing at the right star. The problem is, if any of you have done any astrophotography, or certainly you've looked at astrophotos or through a telescope, you can't see what the telescope's seeing because it's all the light's going into the spectroscope, and all you can get there is a spectrum. You can't see the stars. You can see a few stars in the guide camera, and next slide, I'll show you what it looks like. But there's a slit that prevents most of the light from coming into the telescope. And the reason for that is you want to get just the light from the star. You don't want any other stars or the effect of any other things around it. So the light comes in through a little slit, bounces off this mirror, bounces, hits the grating, bounces off this mirror, goes through a lens and hits the camera over here. But this little slit is 23 microns wide. It's so tiny you can't even see it. This is what the guide camera sees. You see this little black line here, that's the slit. And there's the star we're looking at. And the light from the star has to go through the little slit in order to get a spectrum. So it's sometimes very hard to find the star very hard to get it on the slit and hard to keep it there. That's the hardest part about spectroscopy. You're not taking this great big picture. You're only getting a picture of the light from the star that sneaks through the slit. Okay, here's what it looked like. We were sitting out there on a nice August night. The smoke cleared, which was great. I think you all know we've had terrible smoke down here in the summer. And here's the two students from North Medford, and we're sitting here in front of the telescope, getting things pointed, getting things running, collecting data. But I also can run everything from inside my house, where actually this is the computer I'm sitting at right now, this iMac. And in the winter, I actually don't go outside anymore. I run everything remotely from here. So I've got a lot of software running. I've got software up here running the focuser on the camera. This is running the telescope down here. This is what a solar spectrum looks like. So I'm getting things tested. This is the software that takes the pictures. This is the software running another mount. And now over here, I'm doing photometry. So I've got probably 6 or 8 programs all running at the same time. But once it's up and running, it kind of takes care of itself. And I can go off and watch TV for a while. So we talked about what a nova is, right? It's a star that is igniting. By the way, it's not a supernova. It's not exploding and disappearing. It's still there, but it's igniting. It's getting really bright. Talked about what RSOPH is, that it's unusual. It goes off every 15 or 20 years. It's pulling all this material off the red dwarf. A spectroscope is going to take the light from that star and split it into all the different frequencies. And then we're going to be able to tell all sorts of neat things about the star. So what did we actually see? There it is. Pretty exciting, huh? That's the spectrum. Doesn't look like much, does it? So what this is the light, the slit is actually at 90 degrees to here. And the image of the slit is spread. This is the red side over on the right, and this is the blue side. So it's like that prism, it split the light, and this brightening is the light from the star that gets through the slit. And I don't know if you can tell, but you see a real bright spot right here? And see, here's another bright spot here, and a couple of bright spots, but a dim spot. That's all of the data in the spectrum. And what you need now is some software to pull that spectrum apart and see what's really going on. That's what we're going to look at next. By the way, this was 300 seconds, about 5-minute exposure on the star. And I think I took 8 or 10 of them. So I probably collected, about an hour of data. And then there's software that stacks them all up and extracts the data. So this is that same spectrum. But now, see along the bottom here, we got wavelength in angstroms. And over here is 7,000 angstroms. So this is red at this end. And down here, 3,500 angstroms, this is blue. So if this were colored, this would go from red to blue. And this is by convention, you always put the blue on the left and the red on the right. So this is wavelength. It's split it into these thousands of different wavelengths. This is intensity on the other axis. So this is showing you the intensity of the light on that star at all these different wavelengths. And there's some really interesting things to look at in here. You see all these peaks. Here's one. We'll forget that for a minute. Here's another, here's another, here's another. These are called the Balmer lines, the hydrogen lines of a star, the hydrogen Balmer lines. And what they are hydrogen atoms with the electron jumping a level inside its orbit. And I think you guys have studied enough physics, right, to know that in the kind of the classical Bohr model of the atom, you've got the core of the atom and you have electrons circling and they're in their own orbit or shell. They can jump up or down if they get energy. These guys are jumping because they're being heated up and given all this energy from the explosion, and they are emitting photons in these different frequencies. So this is actually light. Remember that bright spot we saw? That bright spot right there? That's hydrogen alpha. So that is the hydrogen atom boiling away at this frequency. And it's doing it in different frequencies when the photon is jumping out of different shells, depending on what orbit it's going from or to. There's some other things going on here. This is a helium line. So helium is doing one of the same things. These are iron lines, and they are iron ions in this material that are having their so much energy transferred to them that their electrons are jumping up and down, and even iron is emitting photons. So all of a sudden, by looking at all this detail, we can tell a lot about the star. But the most interesting thing I want to point out, and I've sort of zoomed in, this graph down below is a zoom in on the hydrogen alpha line. Do you see anything interesting about the shape of it? It's kind of narrow and pointy here, but it's really wide down at the bottom. Yet I just told you that the hydrogen alpha at 65, 62 angstroms, that hydrogen is emitting energy with this electron or photon jumping at a specific frequency. Yet what this tells me is this frequency is really wide. It isn't one frequency, it's a whole bunch of frequencies. That's for two reasons. Let's look at the bottom first. Has anybody here heard of the Doppler effect? Do you guys know what that is with sound, right? The classical example is like yeah, got a thumbs up there, thanks. So say a fire engine or an ambulance going by, you hear the frequency change as it moves towards you and away from you. Guess what? The same thing is happening here. This broad base here, this is the actual shell exploding off the star, and it's coming towards us and away from us at speeds up to 3,000 kilometers a second. So by looking at this graph, this flat part of the graph is called the continuum. That's the sort of normal part of the star. But if we estimate in here around 3,000 kilometers per second, that's how fast the gases are coming off that star on that exploding shell from day one, at day one. We'll see that changes. So right away, by taking a spectrum, we can get the velocity of the exploding cloud coming off the star. But then what's this sharper peak here? It turns out that's the wind coming off the red giant. And it's coming off at a much slower velocity, so it's not spread out as much. But we are seeing this shell, the collision, and the wind all in this diagram here. And we know how big it is too. So the red giant stuff is about 30 kilometers a second, but this is about 3,000 kilometers a second. So that's just one example of detailed data that you can get from a spectrum. Now, what else could we tell? Well, remember, this is going to change over time, right? And this little diagram at the bottom, somebody took a spectrum before the star exploded and went nova. And this is that hydrogen alpha line again. They're talking about the width of it. They're saying that the hydrogen alpha line is about 20 times wider than during normal time. So red is normal, blue is a little later, the 21st of August. But here, instead of velocity, we have wavelength, and we can see that that has expanded from about 6,600 to 6,520. And if you look up here, I'm going to move you guys out of the way, you can see we're at about, what did I say, 6,600 out here to 6,520. So this is one thing that I like to do. If I've collected data, I could be way off, right? I could have really screwed up something bad. I might be on the wrong star. I might have processed it incorrectly. I like to go to some, this is a published analysis of RSOPH. I like to go to something that's been published and just see, am I in the ballpark? And sure enough, by the way, this was collected with a professional spectrograph, right, at some observatory. My data kind of agree. That tells me I'm on the right track. Now, here's the other thing. The novae evolve really quickly. They change really quickly. And I was fortunate enough to be able to observe this nova 6 or 7 times over the next month. Oop. Get back here. Here's the nova, and I'm going to move you guys again so I can see. There we go. This is a time lapse of the nova over quite a long period, and I want it'll restart when it gets big and growing. That's the very beginning. So hang on, it's just about to restart. Okay, there it is. Look at that hydrogen alpha going way up. But do you notice this? This is that continuum dropping and continuing to drop. That means at the very beginning of the nova, the whole surface of the star was superheated because all that flat area is just the normal photosphere of the star. But over time, as the nova subsides, that goes way down, and eventually, look at hydrogen alpha. It's not only coming down, it's getting thin. Look how wide it is here, and watch it get thinner and thinner at the base. And the reason for that is that that shell is slowing down. Some of it because it's hitting the wind off the red giant, but some of it's just slowing down. So this tells us right away what's happening to the shell of the nova. The other thing is, if we look down here, I don't know if you can see my cursor, but just to the left of H alpha, do you see that little peak? Watch for it. Okay, it's pretty flat there for a while. But watch this little peak start to grow here, right where my cursor is. There it is. See that growing? It's pretty subtle. Little peak growing. That one's really interesting. That's a forbidden line. And I think if you've studied any of your physics or chemistry, you remember ions, right? And that's what an ion is, where it's lost an electron. And you know, there's all sorts of chemicals or elements have ions, and there's lots of ions here. That one is called Fe10, iron 10, which means it's lost 9 electrons. And the reason it's called forbidden is that in normal laboratory conditions, that ion doesn't exist because it is so unstable that it will react with just about anything and change itself. But somewhere way out in the reaches of this cloud of elements being blown out of this star, it is so sparse that Fe10 can exist as a forbidden line. So that's a really interesting thing that pops up near the end, and I guess it's as the gases and stuff blown off the star get way out there. The other thing is, remember I said I like to check my numbers. Here's something called the full width half maximum of hydrogen alpha, and that's a measure of the width of this line. And you can see here on the 12th, it was 46 angstroms, and it's dropping and dropping to the 23rd. So I can actually go in and measure this full width half maximum and kind of compare. Again, this is a professional published result. So what this tells me is, by looking, get back here, at this seemingly not very useful line, there is a ton of data in there, including all sorts of elemental reactions during the during the nova. It tells us the velocity of the shell coming off. It tells us that we can see the wind off the red giant. It tells us we can measure these quite accurately, and we can see the evolution of the star over time. So if you ask why would you observe a nova with a spectroscope, it's exactly for this reason. It tells you a ton about the physics and evolution of the star. So what did I do with all this information? Well, it turns out, as during the introduction you heard, I'm part of a group. We call ourselves small telescope astronomers. That's a bit of a joke. We're amateurs, but we all work with small telescopes. But believe it or not, we have a big advantage over professionals up at like Keck or, you know, any of the big Subaru, any of the big professional observatories. We have time. Professional observers cannot say, I want to take the Hubble Space Telescope or the Subaru telescope and watch this nova every night for 2 months and see what happens. But small telescope observers can. So I belong to a couple of groups. One is called this ARIS group in French. They're a spectroscopy group. And we were able to publish something called an ATEL, Astronomer's Telegram. This is where the fast breaking news comes out. And here's a bunch of the people I work with, David Boyd, Christian Buell. He actually designed the UVEX. But look at, there's me, S. Curry. So I got to contribute my data to an Astronomer's Telegram, which is a professional discussion of what's been happening in RSOPH. And we were able to get that out on the 23rd of August. That was less than 2 weeks after the eruption of this nova. So that's one of the reasons I do this. It's really fun to have your data kind of going to a professional location. So, oh, what's this? TCRB. So that's, remember I told you about the naming, right? T as in ABCD. So it's a variable star in Corona Borealis. And if we look at this, the blue line here is the last time that TCRB erupted. So it's another recurrent nova. The blue dots are observations up till the present. And they seem to be following that curve very, very closely. Outburst is predicted in 2023, plus or minus a year. So that means this nova is going to erupt sometime probably in the next couple of years. So we have already started turning our telescopes to it to get some spectra before it erupts. But you can believe as soon as this erupts, all of us small telescope people are going to be on it. So something more to look forward to. Plus, there will be other novae that we don't even know about yet, of course. There might even be a supernova in our galaxy, and that would be fantastic as long as it's not too close. So that's the end, and I would be glad to answer any and all questions about this topic or any other topic.
All right, before we do that, would everyone please turn on their cameras and their audio and say thank you and clap for Sean? We sure appreciate it, Sean.
You're very welcome.
Yeah, thank you.
Thank you.
Some people put questions in the chat. If you want to read those, go ahead.
Oh, yeah.
If not, then I'll let Brennan read them out loud.
Okay, so here's a question. The difference between a nova variable and a regular Cepheid variable, that's a really good question. The nova results, they typically are binary pairs. And I think you all know, right? Most or a lot of stars are in binary or triplets. And so many novae are symbiotic relationships where one star is pulling material off another star. Once it gets enough, it undergoes some kind of thermonuclear reaction. The Cepheids are varying in luminosity through some internal process. It may be something as they have a shell around them. As the shell heats, it expands, becomes translucent. The light comes out, it looks brighter. The energy leaves, it cools down, the shell goes down, it gets dimmer again. So it's happening within the star itself, not due to material piling on from a companion. Does that make sense? Is it normal to see?
Sean, I'm just going to jump in there for
yes, please.
Since Thomas is a junior, and shamelessly plug myself.
Yes.
So we've only ever offered at our high school a class, Sean, called Earth and Space Science. And it's one semester of space science. It's named backward. But in one semester, and it covers students from freshmen to seniors, you can only cover so much. It's definitely an overview. We're switching next week to earth science, but I got the administration to let me offer advanced astronomy next year.
Good.
So we don't really cover variable stars very well. I kind of barely mentioned them in earth and space science. But Thomas, if you're interested, there's a lot of different kind of variable stars. In fact, variable stars are a fascinating topic. So that's my shameless plug for folks to sign up for advanced astronomy. And then the other thing I'll say there is a big part of advanced astronomy will be doing an independent project, much larger than the independent projects we do in earth and space science. And you could be doing a project like Sean here worked with 2 students from North Medford High School. We have a friend of Sean and mine named Ken Hose, who lives about a 30-minute drive from our high school, who, unlike Sean, is fully retired and has a little more time on his hands. And Ken is always chomping at the bit to have students out to his home observatory and do research like this. So there you have it.
I'll add one thing to that question too about variables. The novae are typically called cataclysmic variables for a very good reason, because there's something cataclysmic going on. By the way, there's a thought that all novae are recurrent, that just some of them are so slow that they may be 500,000-600,000 years apart. There's a lot not known. That's the great thing about this, right? There's a lot of things that we don't know yet. So it'd be awfully boring if we understood it all. Is it normal to see spikes for a heavy element like iron, but not lighter elements? Well, and actually, let me share my screen again, because I didn't really go into that very much. Let me go back to this one. It's a little hard to see here, and I haven't labeled everything, but this one is, this is helium here. So we are getting helium here, and there's probably nitrogen in here. And in fact, there are different classes of recurrent novae. Some of them are called, I think, helium neon, where the helium in neon is much more pronounced. This one had more pronounced iron lines, and actually this is iron, this is iron, this is iron. So this is a classification of an iron type of recurrent nova. So yes, you definitely see the lighter elements, especially helium, nitrogen, and so on. Why there's that distinction, I'm not sure I fully understand, to be honest. And Joe, if you have any thoughts on that, but it's not well understood to me anyways why some of them are different.
It's definitely not well understood to me.
Whether it's the makeup of the star, I guess it's due to the makeup of the star and the makeup of the donor, depending what's coming off that red giant.
I had a question about that. So what causes like each of the elements to produce the different wavelengths? Because I noticed on the previous image there was like iron like 8 or something like that, and iron 2 that were at their own individual wavelengths.
Yeah, so those ones are because the electrons are jumping between different levels. If you were to look at, again, the classical model of the iron atom, you know, the electrons are stacked up in multiple shells, right? So depending on which shell it goes from, it gives off a different frequency. So one thing to take away from this is kind of a golden age of scientific astronomy, right? With fairly straightforward equipment, you can do photometry, spectroscopy, asteroid tracking, and there's all sorts of places for small telescope people to contribute that data to science. So hopefully some of you will get the chance to do that either for fun like me or even professionally as you move along your careers. I would also say to Mr. Minato that if there's a student who wants to do a project remotely, I'm always open to that too. So what I've done in the past is actually used Zoom and allowed the students on the other end to control the telescope via Zoom. So it's almost as if you're sitting there, maybe a little warmer and less smoky, but.
That's very generous of you, Sean. So we might get back in contact.
Yeah, definitely. And I don't just do spectroscopy. I've got another setup doing photometry right now. And as Mr. Minato knows, I've also done a few things with a radio telescope and some asteroid tracking, all sorts of neat stuff. So.
And perhaps my favorite project that my students have done with you is the ongoing Barnard Star project.
Tracking Barnard Star, absolutely.
And students, I want to be careful overcommitting myself or not here, but one of my personal dreams is, I think you know that being a teacher is my life's calling and what I truly love to do, but it's hard. It's hard, and it's hard to have hobbies and raise children and be a full-time teacher. But as my children finish college and are stable on their own, and as I retire from Ida B. Wells, I have my dream of getting as good as Sean at this. That's quite a lofty dream. Between Sean and Ken and this other man named Richard, who often helps, and some other folks, it's sort of my goal to do projects like this, and I'll keep living here in this neighborhood and do them with you. Maybe not in time for you when you're in high school, but maybe when you're in college or out of college. And just letting y'all think about that of keeping the Ida B. Wells High School Astronomy Club growing and doing more and more interesting things when I retire. My great fear is that when I retire, it will evaporate.
The great thing is, though, this is a really good pursuit for virtual teams. The team I'm working on now on these red dwarf flare stars, we have me in Oregon, we've got somebody in San Diego, 2 people in Phoenix, Arizona, somebody on the East Coast, 3 people in England, there's a guy in South Africa. So that's one thing COVID and Zoom has taught us. You can have really productive scientific groups virtually. We meet every week, and we share our data online, and it's definitely something. It's good to get together with people in real life too, but it's also something you can do virtually.
Yeah, I love that.
Well, does anybody else have any more questions for Sean, either about future projects or his presentation?
If you do in the future, Mr. Minato has my email address, so just ping me and I'll be glad to chat with you.
Yeah, absolutely. I had one question about the project. I know you mentioned the distance between these stars was just 1 astronomical unit.
Yeah.
Are most of those, most of these recurrent novae, does that distance usually greater? Is this?
Yes, that is very, very close. And that's why there's a thought that eventually that white dwarf could go supernova, because it's so close and pulling so much material. Yeah, it's got tremendous gravitational effect.
Okay, cool.
Yeah.
All right, well, if we don't have any more questions at the moment, we might as well go ahead and wrap up. Mr. Minato, we still on for the star party tonight at Gage?
Yes. So we are still on for the star party, but I do want to have 2 sort of caveats. Number one, it's really cold out there. So I'll be out there by about 8:25 or so, and bundle up. And the second thing is, I had a very challenging day, unusually challenging day, and I was unable to get to my storage area to get the telescope that I use at star parties. So it's going to be a naked eye star party. I'll have the green laser, and we'll see what we can do without any telescopes, unless any of you who have a telescope who want to bring it off to the basketball court in the northeast corner of Gabriel Park want to bring a telescope. So I want to just make sure that anyone who comes understands it might be just naked eye, but sometimes a naked eye star party is really great, especially when it's cold, is we won't have to stay out too late. And especially since I think you all have final exams tomorrow, it will be an hour probably at the most. It is a beautiful winter night, and there's a lot of really bright stars that I have not had an opportunity anyway to show you before, because we didn't have any winter star parties the last 2 years. So anyway, 8:30, the basketball court, northeast corner of Gabriel Park. I'll be there with my eyes and my laser pointer and no equipment.
Oh,
Sounds
would
good.
it be possible to like grab one of the telescopes like from your room? Because don't we have some functional ones there?
No, all of the functional telescopes are in student hands. The ones that are in my room are all being worked on or waiting to be worked on by the telescope group. And ideally, where I want to get the telescope group is with enough telescopes in students' hands so that I don't have to take a telescope every time. I don't actually have room in my house to store a telescope, so I rent a storage area. And I got distracted with some crises at school today and was unable to get to my storage area. So yeah, so ideally we want to get 8, 10, 12 telescopes in the hands of students who can then provide the telescopes, and also different kinds of telescopes. So you're next on the list, Thomas, for a telescope. How about that?
I'm going to say
I'll be able to
goodnight
bring my stuff.
here, Joe. I'm going to say goodbye to you all right now. So,
Yeah. Excellent,
good-
Sean.
Yeah, good meeting you all.
We'll talk
Thank
to
you
you
so
soon.
much
Bye.
for coming.
Thank you.
Vince, did you have something to say?
Oh, just that I'm able to bring my scope.
Oh, perfect. Perfect. You and
Yeah.
Marina are going to come and bring a scope?
Yeah, yeah, we'll come in.
Also bring the
I've got
like
some, I've got it in storage, but I can get it out pretty quick.
Perfect.
And we'll be there.
Excellent. And
Okay.
so if you're bringing a telescope, the best place to park is in the parking lot off 42nd by the park shop.
Okay.
Do you know where that is?
Not exactly, no. I'm on 42nd by the park shop. I sort of know.
So if you're on
Right.
Vermont Street,
Yeah.
on the north side of the park, turn from whichever direction you're coming, turn south on 42nd. It's just a little tiny road that almost immediately turns left by the park shop where the playground used to be and where
Yeah.
the new playground will be and where the bathroom that's not functional right now is. And then if you park there, it's the least walk. There's a lot of construction going on. They're putting in a super duper new kids playground, which will be
Yeah.
fabulous. But in the meantime, it's just sort of confusing. So we'll be out there looking for you.
Okay.
Yeah, it's
I'll
like
take care of this
between,
when we can. Go ahead.
it's between the playground and the Southwest Community Center. So if you're reaching either of those, then you've probably gone too far.
Okay, that actually helps. I got the location now. And then, thank you. We'll see you
Sounds
there.
good. Cool. Well, hopefully we'll see a lot of you there, and I know I will be there.
Okay.
And with that,
Bundle
nice
up.
meeting
See you there.
everybody. Have a good finals week. Good luck on all your guys' finals, and we'll see you either tonight or sometime at a future meeting. Thank you.
Thank you.
Thank
Bye.
you.
Thank you.